we'll have Bob Stephens, who has some time constraint from Keysight. He'll be talking right now with this talk. Rob, I think everybody knows you. So we have been working with Keysight. I know people mentioned also, I think Mary or others. So he is a key leader in Keysight, and you also do a lot of experimental work. So let's see what new things you have to say today. With that, let's invite Rob Stephens. Right after this, the lunches, there are boxed lunches outside. You can pick it up and go to the cafe and just network and eat. Then we'll be back around 1:10 or so. Please.
Okay, so I'm going to talk about leveraging the O-RAN Fronthaul for spectrum sharing and channel modeling in novel ways. And so we're going to cover looking at how we access the O-RAN Fronthaul first. Second, then we'll take a look at spectrum sharing, data collection, and what analytics we can do that are unique in that location. And then the third thing we'll look at is how to do some advanced channel modeling techniques using that data. And then the last thing is we'll connect the dots and show how to do site-specific channel models for DSS, dynamic spectrum sharing, and how to visualize that. Okay, so Scott talked earlier about the cybersecurity's perspective of the network, and if you look at this network topology here, you'll see that we've got a continuous monitoring framework set up here. This is for a cybersecurity use case, but the key thing here is that in order to do this, you've got TAPs, test access points, packet brokers, and analytics engines. Those are the three key components here. And so what we're going to do here is, and you can see a TAP is basically a test access point that can either be physical or virtual. It can be implemented in software. So if you've got a VM spun up or you got a container and you want to actually get access to that data, you'd have to have a partnership with whoever's implementing that to be able to get that TAP point. Packet broker is basically a hardware accelerator that is filtering packets and routing them to analytics engines that are doing the analytics. And then the analytics engines here are, some examples here are data loss prevention, intrusion detection, or maybe you just want to record the packets to a bit bucket as well. So for what we're going to apply that in a different way. Here, what we're going to do is we're going to apply a fiber tap as shown here, but this doesn't have to be a fiber tap. You could tap off the DU if you wanted to as well in software. And so what we're doing here is we're feeding this data through a tap to this packet broker. That packet broker is connected to a packet capture appliance that's a big storage bucket, and then that's routed to the analytics engines on the bottom, and what's shown there on the bottom are two analytics tools. One on the left is something called WaveJudge that we have that does full protocol stack analysis from complex numbers all the way up through layer 4 and above, past the PDCP layer. And then there's an O-RAN analytics tool there that visualizes the logic on the O-RAN stack. So with both those, we can do something called correlated analytics between the 5G stack and the O-RAN stack. And if you do a search on the Keysight site for O-RAN analytics or correlated analytics, you'll see another presentation that goes into detail on that. Okay, so if you look at the O-RAN interface here at Fronthaul, this is typically what you'd see. This is the Wireshark view. And we see the eAXI flows here, segment IDs, sequence IDs for packets going back and forth between the O-RAN elements. We see the user and control and management synchronization planes. Beamforming coefficients are also flying through this interface very fast. And so that's the typical view we get. And a footnote, if you download Wireshark right now, you would get the Keysight dissectors for O-RAN free. We include them in Wireshark. All right, but it turns out there's a lot more exciting things we can do than just look at the log files for Wireshark on that interface. So one example is the DSS view. We can look at dynamic spectrum sharing, and we can look to see how we can, in novel ways, look at what's happening on the network for spectrum sharing in the DSS view. Next one is we can look at channel propagation quality for your specific network. So instead of just relying on statistical models from the spec to predict what your throughput and data rates are going to be in your performance, MIMO channel ranks and things of that sort, we can actually use this exact same data, looking at it in a different way, and look to see, well, how healthy the propagation environment is for your network. Third one is kind of a slick one. This is based on a paper that I referenced later in the deck here. the OFDM radar view. What this does is it flips the time frequency grid for 5G into a distance and Doppler grid. So basically what you get here is you can look to see what's happening with motion in your environment. So the channel impulse response view, the previous one, you can look at distance, but the OFDM radar view lets you look at motion in the environment as well. And I'll talk about each one of these. Okay, so why is all that stuff important though? So in the context of 6G and even advanced 5G, these networks have use cases now that require either location-specific or application-specific optimizations. And in order to do that, you need some of the data I talked about. Additionally, 6G, one of the key claims for 6G is that we're going to be able to synthesize modulation and encoding types that are unique to your point in space. So in other words, instead of having lookup tables to look up what the modulation and encoding should be for a given reaction that the L2 scheduler is having, we're going to use AI/ML to synthesize at runtime in real time optimal modulation and encoding techniques. In order to do that, you need to have command and control over the channel. You need to have a very detailed understanding of what the channel is. So again, you can't rely on the statistical nature of the spec-based channel model. These channel models look like snowflakes in a way, right? Each one of them is different. Next thing that's important here for this data, why it's important, is that you get a bird's eye view of everything that's on the network from the Fronthaul. You see every one of the UE devices, and you see that through every one of the RUs and through every one of the RU antennas, which is very key for being able to have effectively, and Venki mentioned this a bit previously, having a distributed set of sensors on the network, because now the network is a composite set of sensors that you can leverage here. Two other things to note here, and these aren't standards-based things, but these are opportunities, I think, for future work in the standards. We can extend this to the NTN gateway. So I show here is there a pointer here? It's the right, oh, yeah. The right button is a pointer? Yeah. That's, the right arrow is advancing the slides. Those are a pointer.
Oh, pointer. There should be a pointer here, yeah.
Oh, it's a separate apparatus. Yeah. Look at that. Okay. All right. So what you can see here is I've included in these block diagrams, I've added NTN in here as well. And so for NTN, there's lots of flavors of NTN. There's regenerative payloads where you have the base station on the satellite in the sky. There's gateway-based payloads with bent pipe where the base station's on the ground. Those two in particular, that's where you can use, as Rajiv was mentioning earlier, you can direct to cellular, you can use your phone that you have right now and talk to a satellite. And Keysight's been working with vendors. We have lots of interesting data right now for all these flavors of NTN from space. Well, anyway, we've also done work here where we gather data at these gateways. So you can include gateway data here, just like the Fronthaul I'm talking about. And the next thing here I mentioned was MDT, minimization of drive test. The 3GPP spec has a feature that lets you have devices on the network subscribe to measurement campaigns. Those are pretty basic right now, but if we actually took and connected the dots between our RIC, or mobile edge computing, and some of the measurement campaigns we have there, that would be an interesting combination. Additionally, if you have a private network, there's nothing saying you couldn't have your L2 scheduler tailored to do this without waiting for the standards as well. And then the last thing I'll mention here on this slide is that there's field to lab optimization as well. So what we can do, and we've been doing this at Keysight as well, we can take all this data from satellites we're getting from space, decoding, also terrestrial network data, combinations of the two, and create very realistic channel models that include LEO satellite motion, Doppler and delay, and then mapping that LEO, those LEO beams, sometimes hundreds of thousands of them, to the ground. If they're going over an urban canyon or an agricultural area, whatever, you're going to see different models, so we can model all that stuff. Okay, so let's take a look at the spectrum sharing use case here. So these are some of the typical examples of how spectrum sharing is managed. We have power control, resource allocation in terms of where resources are placed in time and frequency, frequency separation, beamforming not only for directing the beams at the targets, but also directing nulls where you want to have interference mitigated, or incumbent might not want to see what's happening with what you're transmitting. The bottom one here is interesting, coordinated scheduling with multiple neighbor cells. This is something that over decades, the 3GPP folks have worked on optimizing something called COMP, coordinated multipoint, which takes on a terrestrial network, helps you manage co-channel interference by doing joint scheduling between the G node Bs. It was a mention of the XN interface as well, that's where some of this stuff can come into play as well. So these are all techniques that are used to manage the spectrum. So what I'm going to show here now is, this is an example of LFM radar, linear frequency modulated radar. And we have a 5G 40 megahertz bandwidth carrier here running at 3.5 gigahertz on the left. And on the right, we've got an LFM radar signal also at the same frequency, 3.5 gigahertz with a 10 megahertz offset. And if you look at the composite spectral plot on the left, you can see, okay, well, I see the 5G carrier here, and I can see the LFM radar peaking up above that spectrum a little bit on the left side. But you really don't see any more intuitive information about what's happening here. You can't tell what's happening with timing between 5G and the radar. You can't, there's a lot of stuff that's missing from just looking at the spectral plot. So now, if I take a look at the ORAN Fronthaul, and I take a look at that exact same data, only in a different way. Now in the time frequency grid, and this is the vertical axis is frequency, and the horizontal axis is time, and these blocks here are the 5G Lego blocks of data, right? The light green blocks are the pilots for DMRSs for channel estimation, and the dark green blocks are your data. And so what you can see here is you can see that LFM radar signal now, you can see it's got a slope to it. So you can see how its frequency is changing with time. You can see timing relative to the 5G timing and the 5G frame. You can see which physical channels you're near. Are you stepping on any physical channels? Is that happening intermittently over time? Now we've taken a huge leap from that spectrum analyzer plot, right, to this ORAN Fronthaul view that's letting us see what's happening for spectrum sharing. Now, if you look here, this is the PDSCH that's down like share channel burst that's selected. You can see 64 QAM, and it looks clean as the Irish Spring for the constellation. Now, if I go over here and I go select a PDSCH that's actually getting stepped on by the LFM radar, you can see here, okay, the constellation starts to look a little bit like a spiral galaxy in space a bit, right? But we're still passing CRCs where our receiver is correcting lots of bits, so we can tell something's going on, but everything still looks okay here for data rates thus far. And you can see here, you can see that radar signal still popping up above on the spectrum here above 5G. Well, now, if I take and I add in a real-world channel, now I've got multipath. Well, now something interesting happens. Now I no longer survive all those instances where I have overlap between the radar signal and the 5G signal. Now, not only am I correcting lots more bits, I have CRC errors. So sometimes I have errors, sometimes I don't. But if we look more closely, we have an even more intuitive kind of insight here, because we can see that the errors are only showing up on those bursts where the radar signal is present, right, where there's conflict, collision. These here in the middle, we're passing CRC here and there's no problem. Even though the constellation, it's hard for a human to discern what's in that constellation when looking at it. And you can see here, we no longer can see the radar signal popping up above the spectrum, but our ORAN Fronthaul DSS view here clearly shows the radar signal still. So we can still see all the stuff we saw before here, but we can't see it anymore here in the spectral plot. So this is giving us an improved fidelity and resolution. And you can see here, this is the channel impulse response showing we've got multiple copies of the signal for the impulse response here. Okay, so now I'll take a quick look at channel modeling.
We have 5 minutes.
Okay. So in terms of channel modeling here, so traditionally channel modeling looks like this. You have separate equipment from your ORAN network, and what happens is you transmit a signal here. It could be OFDM if you want, whatever. You receive it over here. You put your antennas at multiple points in space, and you move around this whole environment back and forth everywhere. It's a very manual and laborious process. And you do, you look at the expected value of the correlation between what you transmit and what you receive, and you get this H matrix, which is your transfer function for the environment. That's the fingerprint of like this room or wherever you're at for what the transfer function is. Now, this is impractical to do everywhere, but this next method, using the OFDM Fronthaul, is practical. You can do that everywhere. So here again, we're taking that Fronthaul data, and I'm going to show 2 examples of how to get this channel impulse response, one, And then two, how to generate this OFDM radar response to look at motion in the environment based on that exact same data. And we're always parked here looking at that same data. So on the left side here, you can see that these blue boxes represent the algorithm for doing the channel estimation. Basically what happens is the receiver takes these light green boxes, which are the subcarriers that have those pilots for the training sequences that are known patterns. It figures out how to derotate those, and once it knows that, it does a 2D time frequency interpolation here to figure out what to do with your data symbols to correct those. And so, so those steps are done in every phone and every G-Node B. That's not new, but what is novel here is the visualization here of this channel impulse response and the beamforming phase, and also I didn't show here, but MIMO channel rank as well. So this gives us a very interesting set of data now that we can use to go ahead and run AML techniques on to do visually on this time frequency grid. The other one over here, this one is the OFDM radar. What happens here is we do a similar thing. We look at what the L2 scheduler said it was scheduling, and we take what was there versus what we received. And the magic here happens between this FFT, IFFT on that frequency domain data. This gives us an estimate of the variation of phase with time, which basically tells us Doppler. And so that's what allows us to look at speed of targets in the environment, how fast they're moving, and what's happening for location. So now the other interesting thing here is that, as Venki had mentioned earlier as well, what we can do is we can either run this, everything I showed here and everything to be visualized here, we can run this in our AI/ML apps to operate on these time frequency grids to look at all this data on the DU. You can spin this up in the DU, or you could have an adjunct, a mobile edge computing platform over here, tap off the Fronthaul interface as well, and then there's nothing saying you couldn't have that in the network topology connected to the RIC, and then have the RIC consume this data as well, or you can run this on the RIC. Okay, so then last couple things real quick are just to say that, so you can, everything I just showed, you can run all this, everything I just showed, either in a high fidelity digital twin, lab hardware in the lab, or over the air using the network as the sensor, as I mentioned. What I showed here is everything I was showing here, I ran in the digital twin version of this. The other interesting thing I meant to mention before too is that things like spectrum sharing with these radar applications, this is another perfect example for feeding an AI/ML engine, this sort of pattern data as well. Okay, and then last two things are, one, if you wanted to go make these measurements in the field, you could do this with separate pieces of equipment. Keysight is happy to help you do that. We love equipment. But you can also do that by letting the ORAN network be the instrument as well. So you can take all the same software that you would have run on our Keysight equipment over here, most of it, and you can actually use that same software to consume data from the ORAN network here and treat the network as a measurement instrument as well. And you get out of that, for both, either way, you get validation of your propagation models, you get a very rich set of data for AI/ML and 6G applications, long captures, coherent captures across all the antennas, and you can feed a digital twin and iterate back and forth between the digital twin and your real world data. So, okay. Okay? Yeah.
All right, thank you. Any question? Anybody has a question? Yeah, please.
I'm from Viavi Solutions, so competitor, but I hope you can answer the question.
Yeah.
For this excellent presentation, by the way, for this value proposition to work, is that necessary to have it in real time? Because open Fronthaul, you have packets going at gigabits per second. Is the value proposition assuming that it's going to run in real time, or is post-processing offline good enough?
The diplomatic answer would be that you could do both. Streaming is the optimal, right? And consuming that data in real time. Streaming is the most optimal, consuming that data in real time. With some of the tools I showed, could we consume that data in real time and generate those graphs I was showing in real time? The answer is yes. But is there still strategic value in being able to do it in non-real time? Absolutely, I think. Because, things like looking at the channel model, because you can take and immerse these networks, right, in lots of different propagation environments, and you'll learn a lot from that. The other thing is with ray tracing, I didn't show this here. There's another presentation if you look up on the website. Ray tracing based channel models you could do ray tracing for a place you've never been, right? And generate these same sorts of results. So it's a good question. Thanks.
All right, thank you. So